Okay, so integration by parts is a technique, right? And we saw it's pretty helpful. So I'd like to revisit our warm-up problem. That was this one. Integral of x squared e to the x dx. And we did this using 2 iterations of the integration by parts method, right? But let me show you how you can do this with tabular, okay? So evaluate using tabular integration. Okay, so what you do is you just pick part of this to be f and the other part to be g. So I'm going to pick for my f the x squared. I'll tell you in a minute how I know it's supposed to be the x squared. Okay, so then I'm going to label this as f and this is g. And I'm going to make a table. This side of the table is called f and its derivatives. So what I'm talking about is x squared and 2x, which is the first derivative, and 2, which is the second derivative, and ultimately 0 if I take the derivative 3 times. And then on the other column, that column will be g and its antiderivatives. G and its antiderivatives. G is e to the x. What's the antiderivative? E to the x. What's the antiderivative of that? E to the x. And what's the antiderivative of that? E to the x. Okay, so my table runs from x squared to 2x to 2 to 0. So that basically exhausts all the derivatives of f. Make sure you have a table that goes all the way to 0. And then this was actually really simple. All the antiderivatives were e to the x. Okay, then what you do is you draw an arrow from here to here, from here to here, and from here to here. Okay? You're going to be multiplying. The arrow means to multiply. So it looks like we're going to have an x squared e to the x, a 2x e to the x, and a 2e to the x. I just followed the arrows. And then here's the tricky step. Then you're going to put a plus, minus, plus, alternating signs going down. So I'll do that in blue. Plus, minus, plus. You always start with positive. And these become the signs of the individual products that you have. So this will be positive, and this will be negative, and this will be positive. And don't forget the plus c. That's the answer. So why is it working? Well, when you chose your u and dz back in the warm-up, you ended up integrating that dt, right? Which brought you to here. And then you ended up differentiating the u, which brings you to here. See? And since you're always doing ooh minus do, it just basically lays out this pattern, this little diagonal pattern. So you never actually end up using this or this. But watch how powerful this is if you wanted to do like x cubed e to the x. Okay, so let's try another example of this. So let's say you did integral of x cubed e to the x. See, I wouldn't tell you to use tabular. I wouldn't even tell you that on the test. That would just be smart. And the way I know that it'll work, tabular will work, is because this, if you take the derivative several times, it just vanishes. Right? X cubed goes to 3x squared, and then from there to 6x, and then from there to 6, and then ultimately 0. So anytime you have a product of a polynomial term like this, monomial term, times something else, tabular is not a bad choice, because this is going to vanish after a few derivatives, and this allows us to make a table. By the way, tabular means from a table. So let's try it. We're going to let this be our f, and this will be our g, and our 2-column table. F, f prime, f double prime, etc. G, integral of g dx, second integral of g dx dx, etc. So just think of the derivatives of x cubed. What do we got? What's first? 3x squared, and then 6x, and then 6, and then don't forget to do the 0 case, okay? Now let's do our g. This one is the same as the last problem. It's e to the x, e to the x, e to the x, e to the x, e to the x. Okay? Draw the arrow. Bam, 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 bam. This one has 4 arrows, which means you have 4 products. So it's going to be x cubed e to the x, 3x squared e to the x, 6x e to the x, 6 e to the x, and there's a plus c. And then you go in and you put in your alternating signs. So it's positive, negative, positive, negative, positive, negative, positive, negative. And at the end, we always put plus c no matter what. Beautiful method. It's less space on your paper, it's less thinking, and imagine doing this problem by IBP, traditional style. It would require 3 iterations of IBP, 3 choices of U, 3 choices of DD, proof minus do 3 times. So that would be a lot of work, but this wasn't a lot of work. And this is also called rapid repeated integration by parts, or RRIBP. So I'll put that on here too. Tabular is also known as tabular integration is rapid repeated integration by parts. Some people actually don't call it tabular, they call it RRIBP. Rib. Okay. Any questions on that? It's pretty easy actually. Now you don't have to do it on an e to the x problem, you can do it on this problem as well. So let's try this one. Let's do integral of x squared sine x. Actually, let's do something more interesting. Let's do sine 2x, okay? Sine 2x, a little more interesting. So how do you choose the f and the g? Well, you want to choose f so that after a few derivatives it goes away. That's a good choice. X squared is a good choice. Do 3 derivatives and it's gone. Sine x is not a good choice for f because sine x, no matter how many times you take the derivative, it just always is there. You know, it just never goes away. So this will be our f, this will be our g. Let's make our table. I go x squared 2x, 2 and 0. Okay, now let's do the g column. We've got to be careful here. What's the antiderivative of sine? Negative cosine, right? And then we'll need a half here. We have to create something whose derivative really is sine 2x, and here it is. There's a negative and a 1/2 there you might not have thought of. Okay, then we have to integrate that again. We just do it in our head. I think it's going to end up being a negative 1/4 sine 2x this time, whose derivative really is negative 1/2 cos 2x. And then next it's going to switch to positive and it'll become 1/8 cos 2x. Okay, now we'll put in our arrows. 1, 2, 3 arrows for this problem. And multiplying along the arrows, we get negative x squared over 2 cos 2x. And the second one is negative 2x over 4 sine 2x. And the next one is 2 over 8 cos 2x. And then we'll put in our mandatory alternating signs. We've got a plus, a minus, a plus. We'll slap that in here, plus, minus, plus. And then we'll clean it up. Try not to clean it up until you're actually done writing it out, okay? Because you might make an error. So you have negative x squared over 2 cos 2x plus x over 2 sine 2x plus 1/4 cos 2x plus c. If you have the time and patience to check this, it's very rewarding in the end, as you know. Okay, pretty nifty method. Now let's talk about free lunch. Okay, free lunch. Can I move on to the next problem? Okay, so this is called the free lunch method. You won't find that in the book, but it's what my professor called it in college, and I always thought it was a pretty cool analogy. Free lunch is when you get, in life, if you hear the phrase free lunch, it just means something for nothing. That's what it means. Something for nothing. That's why some people say there's no free lunch in life. Okay, but there's free lunch sometimes in math, as we'll see. So the example I want to pick is this one. How would you integrate e to the x cos x dx? See, if you try to use integration, or the tabular integration, here's what's going to happen. You're going to pick, let's say you pick this to be your f. You take the derivative, and it's e prime. I mean, it's e to x, f prime is dx. And then you take the derivative again, and again, and again, and again, and it never goes away. Like, what about Bob in that movie? If you ever saw that movie, Man is Human Crazy movie, it never goes away. So that will never disappear, no matter how many times you take the derivative. And same with this. Take the derivative 1,000 times, you're back to cos x. So it's not going to work to use tabular. Your tabular has to vanish to 0 on one column. Okay, so we can still do IBP, but we're going to find ourselves stuck in this endless loop. Okay, so we're going to start it. Let's see what happens. I'm going to actually pick this to be my u. By the way, I never pick an exponential for my u, if I can help it. I'll never pick e to the x as my u. That's just a general rule of thumb. But I'm going to use IBP. So I'm using u equals cos x, and I guess dv will just have to be everything else. It's right here. E dx dx. Du is negative sine x dx. V is simply e to the x. And I've got my first step started. So I was trying to integrate e to the x cos x, right? And I'm doing uv minus vdu, right? So uv minus integral of v du. Uh-oh. Du is pretty ugly. Maybe we can bring this minus out. Okay, so here's what I got. I am in no better shape than I was when I started. Now I've got to solve the integral e to the x sine x. This is no better than the original problem. It's like equally bad. All right, let's try it again. I guess we'll do another iteration of IVP. Here we go. So, IVP again. Again, I'm going to pick u to be my sine x, dv to be everything else, e to the x dx. By the way, if you chose the trig function last time as your sine x, or as your u, then do it again on this phase. Otherwise, you really will undo all your hard work from previously. Okay, I've been in that situation many, many times. All my hard work just goes away. It's pain. Okay, if you find yourself ending up literally back to square one, then it means you chose the wrong u on your second IBP. That's what it means. Okay, well anyway, I think I'm choosing the right u because I picked cos x last time. So this is cos x dx, and v is e to the x. So let's do uv minus vdu again. Let me rewrite my work here. So I've got e to the x cos x dx equals e to the x cos x plus, and here comes uv minus vdu. Big space for that. So uv, this is just an e to the x times a sine x, minus vdu. Uh-oh. I got e to the x, I can't write. There we go, e to the x. Oh no. Ah, who invited that? Who invited this guy? That's the same integral I started with. But here's the free lunch. You've got one of them over there, and one of them there. Let's add this over to this side. And we'll have two of them. Okay, so watch this. This is like magic. So you add this over to this side, right? Now the left side has two identical e to the x cos x integrals. This side is just e to the x cos x plus e to the x sine x. And then I divide by 2. Don't forget your plus c. So this really is something for nothing, because I never actually solved this anymore. I just IVP'd twice, and I got it for free. That's pretty much. So that's called free lunch. How do you know when you can use free lunch? Well, honestly, a lot of times free lunch comes about when you have e to the x and a trig function like this. Okay? So I laid out your homework so that you can tell what to do on each problem. 1 through 10 is a mixed bag. So some of them you can use Tabular if you want to. That's pretty fast, right? Well, Tabular is super fast. Free lunch on 17 and 19, that's really the only choice. Tabular on 23 for sure. And 38, 40 are multiple choice questions, similar to APS style questions. I think you should do all the multiple choice, but I don't know overwhelm you. So that's going to be Friday instead. Okay? And now you've seen just about every type of integral. The only one that still remains is one called integration by partial fractions. And I'll teach it to you in chapter 8. Okay? And that'll be it for integration.